Hello, this is Jesse Knight, and I wanted to make a brief tutorial on how to use the ILITE Drivetrain simulator that has been evolving over the years. This year, it is more complex than ever because it gives you more information than it ever has before. So to start off, we'll talk about what you should see when you first download the Drivetrain simulator. This spreadsheet has all of its inputs in this left-hand column. A lot of the most basic outputs in the middle column, and your trade-off graphs over here on the right. This spreadsheet is actually meant to be able to be opened up on a 1080p screen that most schools have. And also, if you print the spreadsheet, it should print pretty nicely in 2 pages. So a lot of times if you want to share your design or you want to get questions on it and you contact me, I'll probably ask you to print it to PDF. And that'll give me all the information so I can help you understand what's going on. You'll also notice that the kit apart drivetrain configuration is loaded by default, and there's a couple of reasons for that. First and foremost, I want to help teams understand exactly how powerful the kit apart drivetrain is. And to do that, we will open up these two charts here on the right. Time to goal and the total travel time with stop. The whole overarching theme of this spreadsheet is to help you understand how your robot responds over time. And so what we have here is a drivetrain simulator that actually shows how good the kit apart drivetrain actually is already out of the box. We see that it actually is, a good balance between trying to get somewhere at full speed, 16 feet in this case, and getting there while stopping after we get there. So ultimately, that's what we're trying to simulate with this simulator. We're not trying to say a robot goes this fast. There are simpler simulators that will help you understand that. This spreadsheet is simply trying to help you understand the dynamics of your robot as it moves. So with that in mind, let's go over your inputs. Over here on the left, we have motors. We have a drop down of motors, very simple. We have the Rev and the Falcon in here. We have a mini sim from prior years, and the sim is selected by default. You can put the total number of motors, so if there are 2 motors per gearbox, you would put the total number of motors at 4. You can go from 4 to 6. That's a pretty popular thing to do. But in this case, we'll go back down to 4 because you actually saw some flags light up on the right. We'll go over those in a minute. Gearing. So this is the kit apart gearing by default. This is the Tough Box Mini, I believe. And so you put a 14-tooth pinion on the motor. It drives a 50-tooth pinion. On the same shaft as the 50-tooth gear, we have a 16-tooth gear. And then that 16-tooth gear drives a 48-tooth gear on the output shaft. Combined with a 6-inch wheel, that gives us a theoretical maximum speed of about 13 feet per second. And we can see some other things like your actual gear ratio, things like that, that will help you understand what to buy, or when you want to talk to another team, they ask you how fast does your robot go. This 13 feet per second, just tell them 13 feet per second free speed, and go from there. Wheel diameter, obvious. It's 6 inches. Now I do apologize to anybody who uses metric. I wish everyone used metric, but this is a debate for another time. So 6-inch wheels. I know a lot of teams who do custom drivetrains do 4-inch wheels. You would simply change that here. Or if you're super elite, you'd use 3.5-inch wheels for some reason, and you would change that there as well. Moving down the list, we have coefficient of friction. Now these are usually spec'd from manufacturers. Some teams have also done their own experimentation. Generally speaking, your coefficients will go somewhere between 0.8 and 1.3, and you'll see how things respond accordingly. In the bad old days of 2009, apparently this was 0.12, and you can see that nothing good came out of that. So we'll change this back to 1.0. That's about a good estimation for the kit apart drivetrain wheel. Your dynamic coefficient of friction is the coefficient of friction between the wheel and the carpet once the wheel slips. That is something that is new this year, and is usually lower than your static coefficient of friction, so I estimated it at 0.8. I don't actually know what it is. It could be 0.5, it could be 0.9. If you'd like to experiment with that and get back to me, I will update this by default. Moving down the list, we have the lateral coefficient of friction, and this represents the amount of force it takes to push a wheel sideways. So if you change one of your kit apart wheels to an omni wheel, this would go down to approximately 0.5. If you change it to the blue nitrile tread for whatever reason, this would go up. And you see that not much changes, but actually if you notice this minimum percentage turn output, what this actually impacts is your turning performance. And we can go into more details about that later. Next we have our characteristics about the geometry of your drivetrain frame, as well as characteristics about your center of gravity. These simply help you estimate will your robot turn. And so if I say I have a really long robot, so the wheelbase length between the front wheel that touches and the back wheel that touches, say it's 40 inches and it's kind of skinny, this is really just to help you understand up here, this can turn flag really helps you understand that you might actually have problems turning in the match. So keep the wheelbase length shorter than the width and you'll generally be fine. The kit apart drivetrain does this by default simply because the middle wheel is dropped, so only 4 of those 6 wheels are touching at any one time. Robot inspection weight, pretty straightforward. If your team weighs in at 80 pounds, put that here. If your team is overweight, put that here. Auxiliary weight is typically your battery weight. That's not included in inspection. Batteries are typically 13 pounds, sometimes 13 and a half. And your bumpers are more or less about 40 pounds, 10 pounds. So because those things don't usually change over the course of a season, that's why I separated them out. Sprint distance. So in 2020, we don't know what that sprint distance is yet. But in 2019, good sprint distance was between the player station and the rocket. And the front of the rocket in my case, because we wanted to be able to stop afterwards. In 2018, we actually changed the sprint distance down to 12 feet on ILITE because we were going for the early cubes. In 2017 was a very full field game, so I'd probably change this up to something like 40 feet. You can see how other things respond as you change this as well. I will say that a lot of the output numbers have a big caveat on them. They assume that you actually reach maximum speed before you hit your sprint distance. So keep that in mind. Time to goal. So on day 0, you can estimate how long it's going to take you to go downfield. So we think it would take us about 2 seconds to go from the player station to the rocket. But maybe another team is like, no, we weren't going for the rocket. We were going for the other side. We wanted to come back from the other side of the field playing defense. And so they would say 3.5 seconds to get back. And you can see a couple of things change on the right. Number of times they do in a match. This actually helps you understand total battery usage as noted in this comment. So if you wanted to fill a rocket on your own, you would have 12 cycles, multiply that by 2 because you have to go to and from the rocket, so 24 cycles, or 24 sprints. Deceleration method. This was experimental last year. I've had a lot of feedback, a lot of refinement on this, and this is actually pretty exciting. If you are going at full speed and you throw their joysticks in reverse, you can actually see that the drivetrain decelerates, and it decelerates pretty hard. There's approximately just under 1 G of deceleration there. Conversely, if you set your motor controllers to coast, you can actually see it takes forever for the robot to stop. So brake is the default. Brake's a pretty good estimator of, brake is actually a pretty good estimator of velocity control. Somewhere between brake and reverse is actually what velocity control will entail. So that's why brake is the default. Moving down the list, these are some advanced electrical characteristics. The only one I'll go over in this tutorial is the current limit. That's the most relevant. You actually see that I split it out into the motor current limit, which is in high gear, and the motor current limit that is in low gear. We'll only go over high gear for now. If you want to do 2-speed shifting, you can contact me or I'll describe it on the forums. So motor current limits, by default on PWM based controller, you don't actually have a way to do that on the controller itself. You have to do it very manually using kind of inconsistent power distribution panel readings. So instead, maybe what you want to do is, if you have a Rev Spark Max or a Vex SRX or a Vex Falcon, then you actually have access to this right out of the gate. What that means is, our breakers are only 40 amps, so maybe you want to say, I want to make sure I limit the current to 40 amps per breaker. And so you'd put that in. And you can see how things respond differently accordingly, including increased total time, increased time to goal, that kind of stuff. Right now, we'll set this as 60. That seems to be a pretty good aggressive throttle response. Current limit when you only have 4 motors. There's also duty cycle considerations, so your breakers will not actually see 60 amps for the full duration. So moving to our outputs, we have the pretty standard stuff. High gear, how fast do you go? Tractive force, how much can you push? And then also, when you're pushing, how much current does your drivetrain draw? So back in the good old days when we said you have 6 sims and, my entire breaker would pop because I pushed a robot, well, that's what they mean. I was geared for speed and I tried to push something and I drew too much current and bad things happened. You can actually see minimum voltage goes down and the whole thing browns out, your rubber reader resets. So we'll change this back to 4 for a second. In low gear, if I were to put in a number here, so say I had a 2.0 ratio between high and low, you actually see that low gear changes a little bit. So you pull less current when you push something than in high gear. Okay. Can turn. Earlier you saw me make a really long robot that was very skinny, and can turn said no, you probably cannot turn. So these are just 2 flags. Underperforming means, does your robot take more time to accelerate than you're giving it? So say I had a sprint distance of 10 feet. You actually see that the robot never gets up to full speed. We actually see that acceleration distance is NA because we don't actually get to full speed. So let's change this back to 60. Moving to the right on the outputs, we have our profiles. So we have approximation of acceleration distance, approximation of cruise distance, deceleration distance, and total distance. So total is just the sum of these 3. Now you'll see that cruise and acceleration should match more or less our 16 feet that we want to go for. And deceleration is added on the end of that. Now, I've heard a lot of feedback. Some people want to say, oh, you should be able to estimate deceleration and therefore give us a full trapezoid of velocity. And in reality, to do that, that makes assumptions that the wheels don't slip or you don't hit current limits, things like that. So rather than mess with that and try and estimate all of that in advance, I simply separate out deceleration. If you want to smooth this out in software, you can, so you can get a nice proper profile. And again, that deceleration distance is based upon selecting brake or coast or reverse in your model. This is a good opportunity to show you what happens if your simulator overruns the chart. So you can see that everything stops at 4 seconds. If you need more time, just go down here, hit 5 seconds. It's all good. And you also notice a couple things on the right seem to go off the chart, and we'll go over that in a minute. Now, the main reason I created this simulator way back in the day was because I wanted to understand, as we change gear ratios, ILITE does custom gearboxes every year, we choose which COTS parts to buy. I wanted to understand how that affects time. And so with that in mind, these to me are the primary drivers of what ILITE does to select a drivetrain ratio. Change back to brake really quick. So for example, should ILITE upgrade to Neos on this drivetrain? Turns out that will not serve the purpose of time. No brushless motor will change your time significantly. The driver cannot perceive the difference between 1.6 seconds and 1.8 seconds when going in a sprint. It's like 10%. It's not a whole lot. Now, brushless upgrades are good for other reasons we'll get into in a minute. But as far as time goes, not a whole lot that you change. Not one little thing over here can change time by a whole lot unless you actually change gear ratio. So total time represents the amount of time it takes to get to your goal and then stop after. Your throttle response is the amount of time it takes to go, I'll show the comment here, the amount of time it takes to go from, by default, 50% to 99% of your max speed. This should help you understand that, exactly how much time you're spending trying to get that last little bit of speed out of your robot. You actually see this grow significantly the more aggressively you gear your robot. Minimum voltage is the minimum system voltage that your robot dips to based upon everything that you've selected over here on the left. So we'll go back to the sims and we'll go back to 6. And you actually see that the minimum voltage dips pretty low. And that's this little black line right here, this dotted black line. And you see that it gets pretty close to this red line. And because this is an estimation, I wanted to flag it as soon as possible. So maybe you want to think about not doing 6 sims, or maybe you want to think about current limits, things like that. Let's change this back to 4. And we'll go over these things over here on the right. So turning current, battery usage, and then percent output to turn. A lot of these are driven by kind of your drivetrain geometry and your current limits. So a lot of times this is typically pretty low if you have a reasonably well-designed drivetrain that is not geared aggressively. You know, your minimum percent output to turn is so say you just have open loop control in your drivetrain and you want to give it 8% throttle or 8% turn, your robot will probably not turn. It'll make some noise like it's trying to turn, but it won't actually turn. If you give it 10%, it will probably start turning slowly. And then these values, I would not take them to be literal. I don't expect this to be accurate down to the milliamp hour, but these will help you understand differences between multiple designs as you change things over here on the left. This chart in the middle, movement characteristics, is actually pretty straightforward when you understand it. Your purple line is your distance, your total distance traveled over time. It's a proper S-curve based upon your robot actually accelerating, hitting a velocity, so that's a straight slope here, and then stopping. This black line is your robot's velocity over time. You can see that we go, and then the simulator at a certain point starts to decelerate hard, and you see that this is your deceleration curve here on the velocity. This green chart is your acceleration. You can actually see that your peak acceleration is just under 1g if you do nothing to smooth that out. And same thing when you slow down using brake mode, it's a pretty hard acceleration change, so I would expect your robot to lurch. We see that there are red squares and orange squares for wheel slip and current limiting. This just denotes, when your robot is slipping wheels and when it's current limiting. And you see some changes in acceleration, usually around these points, because the simulator is switching between one limiting factor and the other limiting factor. And we can get into, how to smooth those things out later. Moving down, we have electrical characteristics. So this is the system and applied voltage in the black and the blue. And we have, here we see that we, at the end of the simulator, we stopped, we just let off the joysticks and the robot is now braking. And so the applied voltage drops to 0. Conversely, the system voltage is usually inverse of the applied voltage, right? So it'll kind of mirror it. And we have an actual output system voltage over time based upon what the drivetrain is doing. You actually see that it dips pretty low almost immediately, and then it starts to climb back up as the robot accelerates. This purple line is the current draw of the drivetrain. So with all that in mind, these graphs in the middle represent your actual design. They don't represent any trade-offs. If you change your gear ratio, the entire chart would change. If you change your robot weight, again, these entire charts would change. Over here on the right, though, this is where we get into trade-offs. On the chart on the top, if we were to change the current limit from 40 to 45, what changes? And actually, to show a couple of things that are more relevant with these other charts, I'm going to make a couple of adjustments just because I want to show more real estate. Okay. So here we have, all I did was do a custom gearbox, moderately geared, and I want to show a couple of things here on the right. Now I know a lot of times these charts can get a little overwhelming, and so now you can just turn something off. So we'll hide that for a second. we see that if I continue current limiting down to 25 amps, we actually start losing time. But if I go up to 50 amps, it looks like that's where this starts to flatten out, so I shouldn't lose much more time. But you also notice that the wheels start slipping around 50 amps. I don't know that it's exactly 50 amps, it's around 50 amps. So what we can do is go over here, we'll set this current limit to 50 amps. And sure enough, it doesn't look like it slips too much. It actually starts slipping, so we'll go 52, about 55. Aha, so we see right here, our wheels actually they probably start slipping somewhere around 55 amp current limit, so we'll just do 50. And that's something we can control in software. Now, that's a theoretical, right? So theoretically, they won't slip at 50 amps, but they could. There are ways to test it and actually adjust your current limits appropriately. But you also notice that as I change we'll go back over here, I'll change the current limit back again. Watch these time to goal. So if I change that up to 60, it turns out that the time to goal, they don't really change. So giving the motor more power from the battery doesn't really help much. Conversely, if I change this back down to 40, you lost 1/10 of a second, just current limiting it even more. So time itself is not the reason we current limit. There are a couple of other reasons we current limit, and wheel slip is one of them. Okay. Okay, so hide these. Low gear is interesting. Low gear, if you want to play with low gear, I find it to be pretty cool. You can try and design right up to the edge of traction limiting in low gear. And as long as you get it close, you'll probably have a good year. So what we see here is this black dotted line of system voltage as we change our current limits. And the easiest way to make this ridiculous is to go back to the 6 sims. And we actually see that we're not gaining anything by having an artificially high current limit here. If anything, our system voltage, it's dipping down pretty low by not having any current limit. And so what we want to do to make sure the radio doesn't brown out is just start current limiting it even more. And there are other issues with this design. We won't go into them now, right? It says underperforming, obviously, because we did something ridiculous. Okay. You also notice that it's 18.6 feet per second drivetrain, and we're trying to only go 16 feet. So why in the world would we do that? So we'll change our gear ratio really quick and move down to the next chart. So this chart is the result of some experimentation I did over the summer with profiling and trying to simulate a couple of things. That did not work out necessarily, that experiment, but I did get a lot of cool, interesting insights like this chart. So a lot of times we want to be able to control our robots, especially at max speed. So it doesn't make sense to go 18 feet per second when you only have to go 16 feet. Your robot's not going to go 16 feet in under a second. So what this helps us understand is how long the robot spends at maximum speed, which is this cruise distance, this yellow line here, and how far it takes for the robot to get to its maximum speed, which is this blue line here. This deceleration distance is this gray dotted line, and that helps us understand how far it takes the robot to stop, given everything about the robot we've entered, including the deceleration model. So all of these can help you understand your autonomous performance, and you can make adjustments accordingly. So if you're at a 6:1 gear ratio, you'd actually see that you'd be not at cruise very much. And so if your autonomous had a sprint leg that was like 5 feet, it turns out you're going to have not a very responsive profile for that 5 feet leg of autonomous. So typically ILITE likes to design for a drivetrain that is right where these two meet. If it's a short field, and if it's a long field, we'll design for something else. Also new this year, let me hide these 3 profiles, and I want to kind of address what some teams wish they had this simulator did, and this is kind of a compromise. So a lot of teams say, well, I want to know exactly I want to be able to set 16 feet as my target distance, and the simulator tells me everything I need to do to gear for that. And in reality, that's a little bit more complicated, including wheel slip and current limiting. It's not just a smooth profile that we're going for. So I also, in the simulator, can't assume that every team has access to velocity control controllers. So rather than do that, I wanted to give teams another option, which is this distance in seconds. So we'll hang on for just a second. Over here, we said target time to goal. This was, the strategy team came back and said, we estimate it will take us 3 seconds to go all the way down the field, or 2 seconds to get from the player station to the rocket in our case. So, okay, now we have a way to put that in. And you actually see that if I significantly limit this blue line over here, it actually changes as I change this number. So with that in mind, we can come over here, and what this blue line represents is the distance the robot has traveled at 2 seconds, given the simulation's acceleration, cruise, and deceleration profiles. So you can actually see that at a 6-to-1 ratio, even with the robot trying to stop, the maximum distance the robot travels looks like 21.7 feet. For ILITE, we knew that the rocket, the mean distance to the rocket was about 20 feet. And so that's this line right here. And so we would want to gear somewhere between 8.1 or later, all right? Because we don't want to run into the rocket, so it doesn't make sense to go further than the rocket. That's how we started narrowing in on our final gear ratio. But in reality, it turns out there was something even better. We'll get to that in a second, though. This minimum percentage output to turn is actually pretty cool. This over here up at the top, I mentioned that there's a deadband for turning, where if you output less power than that percentage, your robot probably will not turn. Well, this is that percentage graphed as a trade-off between all the gear ratios you can make. So you can have a stupidly fast robot, but it's also going to take you a lot more power to turn. All right, so let's get into what is graphed per time in 2020. This is something that's brand new, and that is the total travel time to goal with a stop. Now, if you're a defender, you want to go smash into something, you'll let that something stop you, right? And that's this dotted line. But if you want to do offense, and you want to do it with any kind of finesse, you actually want to follow something like this other line here. Now, there are a lot of factors that go into this line, and sometimes this line will change dramatically. But for a typical short field game, this is about right. And you can actually, down below, reference a couple of factors, including Cyberblue's motor testing, back when we were experimenting with 775s, right? And so one of the biggest insights I got into that was it takes about a second for a robot to stop. And so it didn't matter that you geared for your robot to go 50 feet in 3 seconds, right? It's going to smash into the other end of the wall. So I wanted to chart that relative to the gear ratios. And you actually see, we'll go over to the kit-apart drivetrain, you actually see that this is just a picture. This is a snapshot of what the kit-apart drivetrain looks like. You actually see that it turns out for everything that the kit-apart drivetrain is trying to do, it's actually pretty good. It's actually pretty darn close to it's like just a 1/10 of a second or two off the minimum on this chart. You actually also see that you're only gaining like half a second by doing a custom drivetrain. Two big things, and that's, I set up here, we like to design for, somewhere around equal proportion of acceleration and cruise distance, and this is actually pretty darn close. I need to show that as well. This is actually pretty darn close to where this minimum is, right? Somewhere around there. Now I'll hide a couple of things because these graphs can get noisy. Next we'll go into turning current and drag race current. Again, these are just here to show you kind of relatively speaking how much power your drivetrain will draw from your battery. And you can actually see your turning current flatline here, and that's because of your current limits themselves. So if you want to gear aggressively, is going to pull a lot more current to actually move the mass that amount of distance over time. Okay, so we'll hide these really quick. Except for turn current, I want to show you something. So if you notice the turn current here, and I switched to omnis, so I think the lateral coefficient of friction is here, so we'll do 0.5. You actually see your turn current drop dramatically with omnis. So I'll hide turn current right now. And the last thing is kind of this response time. So response time, number one, makes an assumption that your robot gets to full speed to begin with. So this only really applies for everything from like 5.5 gear ratio up. You can actually see that it's not exactly linear. You know, the response time to go from 50% to 100% of full speed for the robot it actually is kind of surprising. You know, the deceleration makes more sense, but for some reason, whether we put a Falcon or a Neo on here, it's not exactly linear. It actually seems to fluctuate for whatever reason. What I'll also do is show you the difference between the brushless motors and a sim. So what I'm going to do right now is change this back to the kit apart drivetrain, because a lot of teams ask me, well, sure, Jesse, you made a pretty fancy drivetrain simulator. Why do I care? What can it do for me? And so we'll go over that right now. We'll do 60 amps for sims because they can take a little bit of abuse. So here we can see our overall drivetrain graph in its entirety, and we see that it's going to take, we actually see the number right here, it's going to take you 0.9 seconds to go from 6 feet per second to 11.8 feet per second. Just changing the sim to any brushless motor, so we had the Falcon up, but now we'll do the Neo for a second. You actually see that time drops by, about 33%, which a driver can't perceive the amount of time, but a driver can understand. The driver does perceive, I told the robot to turn and it did not turn. It seemed to lag. And sometimes that is actual lag and sometimes it's just physics. So you'll actually get a pretty good response time. You also saw that the theoretical max speed jumped a bit too. So not only with brushless motors are you going faster, but it will respond better. Let's also put in the Falcon just to kind of demonstrate. You actually see the throttle response did not change. However, the robot's also going pretty significantly faster. So if we were to change something about the gearing, which you can't do this with the kit apart directly, if we change the gearing to be approximately what the Neo was, you do see a drop in the throttle response time itself. So again, when people say, "Oh, it's about a 5% increase over the Neo," it actually is kind of true. It's just more, can the driver actually take advantage of that? But I would definitely say that a sim to either brushless option is worth the time and money invested. In closing, I'll leave you with a couple of other things that can be tweaked and tuned on this simulator. So down here, maximum time. For a full field, you'll definitely want to increase to like 6 seconds, just because we need more time to simulate all of the various gear ratios. So say we wanted to go 40 feet. A lot of the gear ratios need more time for simulation, so just increase that. Your minimum gear ratio, again, these just affect the charts. So say it's a stupidly short game, you can just change that to like 17 and you'll see more simulation at a higher gear ratio. This one, when we say that a robot does not hit its full speed on a field, so it's never going to hit 13 feet per second, that is usually true. There are a couple of other things that kind of go into that calculation, but basically what this says is we wanted to set the simulator needs to know when the robot has stopped accelerating, when it's actually at max full speed. And so this is the feet per second acceleration that this green line must dip below for the simulator to say, yes, I'm at maximum speed. And then throttle response, so say you wanted to change this around, you wanted to see kind of from 0 to 100 what the throttle response is. That's how you do that. That's it for this tutorial. I know it was very long. I'm very sorry that this is a pretty complicated spreadsheet, but hopefully it gives you a lot more information than it used to. and hopefully you find it valuable. If you have any questions on it, I am in the FRC Discord. I don't have private messaging turned on from that Discord, but if you ping me in that channel, I will try to respond as soon as I can. Thank you.